Hello everyone. In this video, I'll talk about how to solve the AP Physics C Mechanics Free Response question number 3. You'll see again, like in this solution here, sometimes I will talk more than just the questions. I will talk about the concepts that is behind the question they are testing you. Okay, so let's first look at the question and then we'll talk about how to solve them. A system consists of a small sphere of mass m and radius capital R at rest on a horizontal surface, and a uniform rod of mass capital M, which is 2m. We're going to use that later on to simplify the result, and length L attached at one end to a pivot, that's right here, with negligible friction, where capital R is far less than the length of the rod. There's negligible friction between the surface and the sphere to the right of point A. So you can think about this section here is smooth. However, when the ball passes this point A, there will be a rough surface, so that there will be friction force here acting on the ball. Now the rod is held horizontally as shown in the figure 1. In this figure 1, then it's released from rest. The total rotational inertia of the rod about the pivot is 1/3 ml squared, and the rotational inertia of the sphere about its center is 2/5 mr squared. After the rod is released, the rod swings down and strikes the sphere head-on. So usually when we say head-on collision, it will mean that the result of such collision is one-dimensional. So the rod center mass velocity going this way, right, to the left, that will be the direction of the sphere's final velocity direction, right, leaving the collision site. So now, as a result of the collision, the rod is stopped and the ball initially slides without rotating to the left across the horizontal surface. The reason it's sliding without rotating is because the surface here is smooth, so there's no torque due to friction to rotate the sphere. So the sphere will simply just slide right on the surface. Question A. Derive an expression for the angular speed of the rod just before striking the sphere in terms of the length L and physical constants as appropriate. Okay, I'm going to draw a similar diagram here for part A. And right now, because it only concerns the rod, so I'm going to just draw the rod. So here's the rod at the horizontal position, and you'll see that because there's no friction on the rotation axis, so the energy is conserved. So the total mechanical energy of the rod is a constant. And if I say this position is the initial position, and then when the rod is vertical, that position will be called the final position. Okay. Now I want to write down the mechanical energy of the rod. So I need a potential energy, a zero potential energy level. So I'm going to say is at this dashed line, which is the ground right here. So that is the origin O, and the y-axis must be upward. Okay, so that's why we can write down, so EI equals E final. That's why we can write down the initial and final potential energy, right? You always need to define a reference point, which is the origin, before you write that down. So initially, the rod is at rest. So the only energy we have here is the potential energy, which is the total length here is L, right? So the center mass here, that's the center mass of the rod, is at a height L above the origin. So it's mgl. That's the initial potential energy of the system, and there's no kinetic energy at the beginning. Now at the final position, Now the center mass is here. That's half L above the origin. So let's write down mg half L as the potential energy of the rod at the final position. Now, because now the rod is swinging this way, suppose its angular velocity is omega. Let's see the symbol. Yeah, okay, didn't say anything. So now let me say it's omega naught, because I want to consider the collision later on, and I want to call that initial angular speed. Okay, so that's why I can write down 1/2 I rod omega 0 squared, omega naught squared. Okay, so let's substitute in the moment of inertia for the rod, which is 1/3 ml squared. Okay, so now we can rearrange the terms. So the left side will be 1/2 ml mgl equals the right side is 1/6 ml squared omega naught squared. So the mass cancel out. We'll get omega naught equals 3g over L. So one of the L will also cancel out. That's one of the L. Okay, so that's the first question. Now, second question. Derive an expression for the linear speed v0 of the sphere immediately after colliding with the rod in terms of length L and physical constants as appropriate. Okay, so now we should think about angular momentum conservation. Okay, so if you draw the, let's say, the free body diagram for the two objects, right, at this instant, right at the collision instant. Okay, now for the rod, there's going to be gravity and the normal force. So one thing to be careful about the normal force is that the normal force now is not along this vertical direction. It should be along this direction here. So it has a horizontal component, not just the vertical component, but also horizontal component here. That will change the total momentum of the system, linear momentum of the system. So system here is rod plus sphere. So the linear momentum of the system in this process is not a constant, it's not conserved. So you cannot use the linear momentum conservation in this question to solve the problem, to figure out the velocity of the sphere, right, after the collision. If you use that, it will be wrong. And the reason for that is because there's a n horizontal component. Okay, so that does not conserve. That makes this P system, the linear momentum, not conserved. However, if you think about the angular momentum, then you'll see that all the external torques, so that's one thing I didn't draw here, little mg, that's the external force acting on our system. So notice I didn't draw the interaction, the action-reaction between the ball and the rod, because that's internal force that will not affect the total linear momentum or the angular momentum. Okay, so the torque due to little mg, the net torque of the system, sigma tau, so that's net torque or total torque, would be torque due to mg, little mg, plus torque due to capital Mg, plus torque due to normal force. They all equal 0, right? Reason for that is because here's the rotation axis. The axis is right here. So N goes through it, gravity Mg going through it, capital Mg going through it. Little mg also goes through it because of the relation that R is far less than L. Okay, so that means that there's no devil arm for little mg. So that's why all three terms are 0. The torque due to all three forces are 0. So that's why we have L system equals a constant. Okay, so now with that, let's write down the angular momentum conservation. So before the collision, we know the angular momentum of the system is due to the rod rotation. So that will be I rod times omega naught that we wrote down earlier there. This is solution here. So that equals the final angular momentum of the system. So the final angular momentum of the rod will be 0. Because the question says that after the collision, the rod stops. The rod is stopped. So that's no angular momentum. Okay, and the only angular momentum is due to the sphere's linear speed v0. So let me represent that v0 here. That's v0. Okay. Linear momentum, linear velocity here. So that will give us an angular momentum for the sphere. The length L here, little l here, multiply, and we know. Okay, so remember for a particle, the angular momentum is defined as R cross P. Okay, so R cross P. The R represent the position vector pointing from O to the object, to this point particle, the small sphere here. And then cross P, P is MV naught. Okay, so they form 90-degree angle. So that's why the magnitude here is L, the length, the distance of the length of the rod, times MV. Okay, so that's the magnitude. And direction is going is the counterclockwise direction. It's the clockwise direction. So it's the same as the direction here, omega naught, which is also clockwise. Okay, so now from here, I can calculate V naught equals I rod omega naught over M little l. Now let's substitute in the I rod expression 1/3 capital M L squared omega naught by square root 3g over L, and then little m times L. So now we see some cancellations. Little l will cancel with this one of the L. Little m will cancel with this capital M. We have a 2 here, 2 left here, because capital M is 2 little m. So now with all that, the V naught here is given by, in the end, is given by square root 4GL over 3. Okay. Okay, question C. After sliding a short distance at time t equals 0, the sphere encounters a region of the horizontal surface with a coefficient of kinetic friction mu beginning at point A. The sphere begins rotating while sliding and eventually begins rotating without sliding at point B. Now question C, in the following diagram, which represent the sphere while the sphere is traveling between point A and B, draw and label the force that act on the sphere. Okay, each force must be represented by a distinct arrow pointing away from the point of application on the sphere. Now question C, it's about free body diagram of sphere. Now here's the sphere. Okay, now of course, first one we think of is the gravity. Right? Gravity is acting at the center, right at the center. Now the normal force, right, exerted by the ground on the sphere is on the bottom point, right? So I'm gonna like displace this one a little bit so that you can see the acting point is right here. And the direction is vertical. So I'm going to draw a better one. It's normal force. So it should be understood as going through also the center, but again, I displaced it a little bit. And the length to be equal to mg, the length of the gravity. Now, the friction force on the bottom will be backward. It's actually kinetic friction, right? Because it's sliding, right? Sliding on the surface, so it's Fk. And the direction is opposite to the velocity. The velocity is this way, right? So that's why it's to the right side. Now question D. Derive an expression for each of the following as the sphere is rotating and sliding between A and B. Okay, using V naught, mu, R, and T, and physical constants. The linear velocity V of the center of mass of sphere as function of time. So now we have the free body diagram. So we can write down Newton's second law. But before I do that, let's review a little bit of rigid body dynamics. So you want to write down Newton's second law for linear motion. So you want to write down net force equals ma. Okay. And for rotation, so that's for the sliding V. Now for rotation, you want to write down net torque equals I times alpha. Okay, so we're basically doing this right now. So the net force along this direction, now let's say I pick the positive x direction to the left side. That's positive. Then the force here will be negative. So the net force is negative Fk equals ma. Okay. Now Fk here is related to mu times normal force. That's the definition of Fk. And n is mg. Okay. So we can combine them, and then negative mu mg will be ma. So that's according to Newton's second law, we can calculate the center of mass acceleration is negative mu g. Okay, now let's relate this to the velocity, the linear velocity at any instant. So we know v, according to kinematics, is v naught plus at. Now let's plug in a equals negative mu g times t. So that's the function of the linear velocity as a function of time. That's part one. Now part two. Now we need to study the rotation, right? So we are going to use this equation here. So sigma tau, the net torque with respect to the center, both gravity and normal force give zero torque here. The only torque we have here is torque due to Fk, which is R times Fk. Okay, and it's also like counterclockwise. You will introduce a counterclockwise rotation. So the sign here is positive. Okay, equals I alpha for this one for sphere. So I'm going to label that IS. And let's substitute in fk, which is mu mg, okay? And is here is 2/5 mr squared times alpha. So we can calculate alpha equal angular acceleration equals 5 mu g, 5 mu g, and r, this r will cancel out with one of these r here. So it's 5 mu, and also m cancel out, 5 mu g over 2r. That's the angular acceleration alpha. Okay, so now according to kinematics, the angular velocity omega at any instant is the initial, which is 0 here, because at the beginning it's not rotating, plus alpha t. So that's why it's 5 mu gt over 2r. So that's the second question here. All right, so let's look at the now let's look at the last question. Question E. So you ask about deriving an expression for the time it takes the sphere to travel from point A to point B in terms of mu naught, v naught, mu, and physical constant as appropriately. The property of point B, remember it says that at least point B here, the sphere here will slide without, will roll on the surface without sliding. Okay, so that means that it's the case of loading. So at B, the sphere will start to loading without sliding or slipping. Like some textbook says it's slipping, loading without slipping. And that is testing you about your understanding of the loading motion. So for the bottom point, V bottom, its velocity is the center of mass velocity plus rotation around the center of mass. So the rotation around center of mass will introduce now in this case rotating that way, right? So we introduce rotate the other way around. Well, in this case, it will rotate in this way. This would be omega, right? So omega rotation will introduce a linear velocity r omega this way to the right side. So they should cancel out. Okay, meaning at this instant, the linear speed v would be linear velocity v would be equal to r omega. They're opposite in direction, but their magnitudes are the same. So that's why v equals r omega. So now with this condition, let's look back at the previous expression. V equals v naught minus mu gt. And r omega equals this quantity here, 5 mu gt over 2r. From this equation, we can calculate the time instant when they are equal, right? So that's the time we're looking for. So let me group all the t terms together. So first I'm going to cancel out this r here. Okay, so we have 5 halves plus 1. So that's 7 mu gt over 2, right? Yeah. Okay, so now from there, I can calculate the t here is 2 V naught over 7 mu g. So that's the instant when the sphere here roll without slipping. That's the instant we're looking for. Now, second part, derive an expression for the linear velocity of the sphere upon reaching point B. So we can substitute in this t here in the equation for v, right? So v equals v naught minus mu g, and let's substitute in this time. Okay, so now you'll see it's mu g cancel out, so we have 5 v naught over 7. Okay, so that's the answer. Now, as a check, so if you have a time, like let's say during the exam, since this one is already the last question, you want to check, right? So now how about let's check with another method for calculating this final velocity. So we can use angular momentum conservation for sphere. Okay, so right at the instant when after the rod hit the sphere, the sphere has velocity v naught, right? So if I think about, let's say, in the whole process from moving from this position to that position B, if I use this point as the rotation axis O, then the angular momentum with respect to O will be a constant. Okay, so at the beginning, we should have the initial momentum is r times mv naught. Okay, so you can figure that out like using r plus mv, and you will get this number here, this expression here. Now at the final position, the angular momentum comes from two contributions. The angular momentum of the center mass, which is rmv. V is the one that we need to figure out the final velocity, plus the sphere rotation along the center mass contribution. So that's omega, right? I as omega. And since we're interested in V here, so let's replace omega by V over R, right? Because that, again, it's this relation here, loading without slipping. So now IS is 2/5 mr squared. Okay, so if you rearrange all these terms, you will find that V is the same as this one. So that serves as a check of your calculation, previous calculation, but of course in the condition that you have time left. Okay, all right, so that's all for the third question of the AP Physics 2023 mechanics exam. Okay, thank you for watching.